Hello everyone, and welcome to the video lecture on the geometric distributions. So I think by now we've spoken about the binomial distribution and the uniform distribution in the context of random variables, and how we can use them to talk about what the probability that our random variable is equal to certain subsets of its sample space. And next we're going to talk about another distribution that we can use to model random variables called the geometric distribution. So let's go ahead and jump right in. Boom. So let's start with sort of how we want to think about it by means of an example. Suppose you flip a fair coin until a flip comes up heads. Let our random variable x be the number of flips until heads. Yeah? So, I mean, before I even give you the formula for the distribution, just think about how much of an interesting probability problem this is. So I could flip one coin and immediately get heads, which means the value of x would be 1, or I could flip 50 coins and the first 49 are tails and the 50th is head, in which case x would be equal to 50. So let me write that out. Note that x equals 1 corresponds to the first flip is heads. Which, note, this is pretty likely. There should be a 50% chance of this happening. X equals 2 is we flip tails, then heads. Also likely, right? That seems a very reasonable situation to happen. I flipped one, I got tails, the next one was heads. Boom, x is equal to 2. I would observe that and I would be like, yeah, that's how a coin works. And we could keep going like this. X equals 3, 4, 5, 6. And we could even have something as large as x equals 1,000. Which means we would flip 999 tails, then heads. And note that this last thing is very unlikely, but possible. I wouldn't expect this to happen, but certainly if, I don't know, Lady Luck smiles on you, that could just be what happened. Maybe Lady Disluck, I don't even know. So, and I should actually put another ... right here because we wouldn't necessarily stop at 1,000. Yeah, 1,000 is so unlikely, maybe we wouldn't even assign it a positive probability, but it could still happen. And we have to figure out a probability distribution that sort of accounts for all of these different scenarios. And without further ado, maybe I'll just give it to you, which is the probability that our random variable is equal to some value k is equal to 1 minus p to the k minus 1 times p, right? And think about this. This is actually kind of intuitive. So wait, maybe I should, goodness. Maybe I should mention two things about this. So k here is the number of flips So if I wanted to know the probability that I get heads on the first flip, or probability that the first heads I get is on the third flip, the latter would be probability of x equals 3. And P is the probability of success. So in this case, note that we've set, since it's a fair coin, the probability of success is 0.5, right? But it doesn't necessarily need to be. And in fact, this distribution can also be used to model cases where the probability of success is not a coin flip. It could be something less. So maybe like, I don't know, a loaded coin where heads comes up 0.1% of the time, or maybe I'm doing some sort of process, like I'm fixing a bunch of cars and I know 10% of the time I fail to fix the problem, and we're trying to see how many cars do I fix until I first fail to fix a problem, right? It doesn't necessarily need to be coin flips, and P doesn't necessarily need to be 0.5. So we have these two values, K, which is sort of like the input that we put in to see what the probability is, and P, which is the probability of success. And note here, I'm gonna write this again. This is like our formula for figuring out problems like these. And note, the formula is actually kind of intuitive. If I want to know the probability that my first success is at K, so like maybe 10, we could pretend K is 10 here, then I would times by the probability that I don't get it, and then I do get it once. That's kind of the intuition behind this formula, and it's the formula for calculating probabilities in a geometric distribution. So one thing I want you to note about this, maybe actually I'll put this note a little later. Okay, so we have our distribution. Let's use it on this problem. So what's the probability that my first heads is 3, is on the third? So that would be the probability that my random variable is equal to 3. The first heads I observe is my third flip. Since my coin is fair, I'm going to plug in 0.5 for P, plug in 3 for K. What is this? 0.5 to the 2 times 0.5, which is, let's figure that out, which is 0.125. So this is the probability that if I'm flipping a coin, that with 0.125 probability, the third flip is the first heads that I observe. Pretty straightforward. So something to note here. This is a discrete distribution. Which means that probability at a point is meaningful. So recall whenever we were dealing with probabilities of a continuous type, if we want to know the probability at a single point, like if I want to know the probability at 5, this was always equal to 0. Whereas the geometric distribution, and unfortunately I need to own that I didn't grab this before class, so let me grab it real quick. geometric distribution actually looks something like this. And it's a discrete distribution, so if I wanted to know the probability at a certain point, that actually has a meaning, right? I can actually find that probability. It's what looks like here at 0.14 or something like that. Okay? So geometric distributions, unlike our continuous distributions, you can actually find probability at a point, which is, I thought, was a worthwhile point to make. Point to make. Okay, so this is what our geometric looks like. And I'm just going to give you this fact that, like all random variables, the geometric distribution, you're able to calculate its expected value and its variance. And you could actually calculate them if you used, what was it? The expected value equals x times p of x equals xi. Right, this crazy formula to find the expected value, and there's also the same one for variance. There's also the one for variance as well. Right? If you use both of these formulas on the geometric distribution, you could actually go ahead and solve for which of these values are. But I'm going to give you this fun fact. That I'm going to do that math for you, not require that you do it. And I'll tell you that the expected value of x, where x is geometric, is a geometric random variable, is 1 over p. And the variance of x is equal to 1 minus p over p squared. Okay? So this is the expected value and the variance of a geometric random variable, which a random variable is called geometric when it is specifically this scenario that I covered at the very beginning. So if your random variable, it describes a process like this, you can call it geometric, and you will therefore automatically know what its expected value and its variance is, what it looks like, and how to calculate probabilities with it. Okay? This is really just a sort of like recognize the process and know the formula kind of situation. So I have a, oh, I already did that. Okay. So I have another example. Suppose we discovered that the coin isn't fair. In fact, heads occurs with only a 20% chance. What's the probability that our first head happens on flip number 2? Well, this actually isn't that hard. We just need to plug it into our formula. X equals 2. The probability of success, in this case, the probability of getting ahead is 0.2. So what we do is we plug in 0.2 now for P, plug in 2 for K. This is actually just equal to 0.8 times 0.2 or 0.16. So the probability of the second value being heads, given that our coin is unfair, is 0.16 in this case. So that's just another example for you. So, next example. With the same coin, so the unfair one, what is the probability that our first heads happens at or before the third flip? Well, if we were to write this, this is the same thing as saying what's the probability that x is less than or equal to 3, which we would want to say is, that is true if x is equal to 1, or if x is equal to 2, or if x is equal to 3. And the thing I want you to note is that these three events they're actually disjoint. Because think about it, if event 1 happened, if my first flip is a 1, then event 2 can't happen, right? My first flip is a 1, my first flip can't also be a 2. And that also works the other way around. If my first flip is the 2, clearly my first flip wasn't the 1 because it's implicit in saying that the first flip wasn't a heads because I'm saying my first flip was a 2, right? So these events, these three ones, are disjoint just as a consequence of the definition of our geometric distribution. And because of that, we can use what we know about disjoint events to say, this is just the sum of these three probabilities. So what is the probability that x is equal to 1? Well, that's something we can just plug into our formula for the geometric distribution. So 1 minus 1, and then this is 0.2. And what is the probability that x equals 2? That is, again, just a plug and chug with our formula. Classic plug and chug. What is the probability that x is equal to 3? 1 minus 0.2, 3 minus 1, 0.2. So this is equal to 0.2 plus 0.16 plus 0.128, which is 0.488. That's the answer to this question. So, do I want to keep going or do I want to end here? All right, I think I've probably droned on enough about the geometric distribution. I think there's one other thing I might mention, but I'll just use that for my next lecture. So thank you, everyone.